Hello everyone, here's a video on calorimetry and the calorimeter and the calculations all that are around that. Whenever we want to measure the heat flow between two substances, we have to have a very careful situation, a very controlled situation, and our system is going to be very defined here, and that's going to be what's called the calorimeter. And the calorimeter could be as simple as a styrofoam cup with a lid on it, or it could be more complex, such as something called a bomb calorimeter, which is what the food industry uses to measure calories in food products. So when we get to, in order to study calorimetry, we must first talk about heat and the fact that heat flows, and also the fact that everything has its own gain or loss of heat. We call that specific heat capacity. So the specific heat capacity, I'm going to ignore the definition for heat capacity right now and get a little bit closer here to what we need. For pure substances, that means any pure substance will have its own specific heat capacity. In other words, it's the amount of heat required to raise 1 gram of that pure substance by 1 degree Celsius, or perhaps 1 Kelvin. It's the same thing. Okay, so again, 1 gram of 1 degree Celsius, 1 gram of 1 degree Celsius. That's the amount of heat. And since it is a pure substance, this is like density. This is an intensive property where it's just part of the substance. Okay, the equation that we're going to use, actually, there's two equations. The first equation that we'll use is going to be, I guess it's down here. There it is. This is called the specific heat equation. Okay, Q equals mc delta T. Q is enthalpy. Is Q and delta H are the same thing as long as it's measured under constant pressure, which most of the stuff we will do is measured under constant pressure. So you can see M is mass, C is specific heat. That's measured in joules per gram times degree Celsius. I'll write that out for you. So specific heat is joules over grams times degrees Celsius. That could also be Kelvin, okay, because it's the same thing. Well, the change is the same thing. And the delta T is, of course, final minus initial temperatures, okay? Now, this is the equation that we will use most of the time, okay, this equation. They're going to give you mass. I have seen it pop up every once in a while, so you should be ready for it. The molar heat capacity. So instead of the specific heat capacity, I'll give you the molar heat capacity. And again, you can see here it's just the same thing, except instead of mass, it's moles. So NC delta T. Now, if we were to do a couple equations on here, they're actually quite simple, at least these initial ones. So how much heat is needed? So Q, to warm 250 grams of water, 22 degrees Celsius, to near its boiling point to 98. So if we're going to solve for Q, we have a mass, and the mass is 250 grams. And then the specific heat, the specific heat of water you need to memorize. Okay, make sure you get that in your brains on the test, in your notes somewhere. Okay, 4.18 joules per gram times degrees Celsius. So I'm going to get rid of that and plug that in here. So the specific heat of water is 4.18 joules per gram times degrees Celsius. The grams cancel so far. The delta T, final minus initial, 98 minus 22. I believe that's 66, but I'm just going to clarify with the calculator. 98 minus 22. I put it 78. Excuse me, 78. That's not right either. 98 minus 22, 76, 76 degrees Celsius. And now we just multiply. We're left with joules. That's where we want. So 250 times 4.18 times, 4.18 times 76 gives us an answer of 79,420. So that would be our answer in joules, 79,420 joules, okay? I could move that to 79.4 kilojoules if they ask for it. Either way, I just move the decimal place over 3 places, okay? So either way, either answer is correct as far as that goes. Now, we'll go over this in class. Again, we'll use MC delta T for that one. And here's another one. It says a large bed of rocks is used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82. Calculate the quantity of heat absorbed by 50 kilograms of rocks. So again, I'm not going to go over this one now. I'll do it in class. But essentially what we're going to do is just use Q equals MC delta T. So it's asking for quantity of heat. The mass, though, is 50 kilograms, so we got to change that to 50,000 grams, okay? So if I plug that in, that's that. Now the rocks 0.82, there it is. Delta T, we want increases by 12, so we got that number too, okay? So all three, plug and chug, we should be good on that one. Okay, we'll go over multiple choice problems in class. Okay, now this one's a little bit different here. Okay, so let's take a look at this. When a student mixes 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH in a coffee cup calorimeter, the temperature of the resultant solution increases from 21 to 27.5. Calculate the enthalpy change for the reactions in kilojoules per mole of HCl. Okay, so it seems there's a chemical reaction here. I don't know if I'll use it, but it's always good practice to do this. So I have HCl plus NaOH yields NaCl plus water. Okay, and it's balanced. Forget that little slash there by the NaCl. Okay, so it's all 1 to 1, so I think we're okay with the balanced equation. But what I need here is, let's see here, calculate the enthalpy change, so the delta H, which is the same as Q. So what I'm going to do is use Q equals to M times C times delta T. Okay, so we'll start with that. So I have a mass. Now here's the thing, guys. Whenever I have these volumes here and here, because water is so abundant in a 1 molar HCl solution and so abundant in a 1 molar NaOH solution, we're actually going to use the specific heat of water. We're actually going to use the density of water, okay, to solve this problem. So notice we don't have the mass listed here. But I do have 50 milliliters and 50 milliliters, and since I just mentioned that we have so much water, let's use the density of water being 1 and convert 50 milliliters to 50 grams. So don't put 50 under the mass, you're going to put 100 because you're going to combine it together. Okay? And then we're going to use 4.18 joules per gram times degrees Celsius times the delta T, which looks like it's 26.5. And we'll get an answer. It's basically 100 times 4.18 is 418 times 26.5. And we end up with 11,077. Okay, that's joules, by the way. Okay, let's move on. All right, we'll do this class demo if we need to. This is a bomb calorimeter. Okay, so a bomb calorimeter is actually quite cool. What they do is they take a food stuff in here, some type of food, put it down below here, and then what they do is they turn on electrical current, and that causes this stuff to ignite. So it starts to flame up. Okay, and as it flames up, it heats, it burns, and what it does is emit heat to the water. This is a carefully controlled amount of water in here, and if they know how much heat goes from here to here, and they know the mass of this stuff down here, that's Q equals MC delta T. But they're measuring the water, so they're actually measuring the water, the heat transfer to the water. And there's the thermometer that measures that, okay? So yeah, that's how they get calories. Okay, now I want to do one of these problems because it's a little bit different. And you saw this, you can see this in any typical video. But what we need to discuss is that when we talk about two things being, one thing cooling down and one thing heating up, we know that the cooling down is exothermic, and we know that the heating up is endothermic. Notice I made them equal because if I put them into the same system, in the same coffee cup calorimeter, we have the heat lost by one is equal to the heat gained by the other, assuming that the calorimeter didn't absorb any energy. And we'll make that assumption every time. Okay? So the heat lost by one is equal to the heat gained by the other. Okay, so let's keep this negative Q is equal to positive Q in mind as we solve this particular problem. Okay, so what we have here, a lead pellet having a mass of 26.47 grams at 89.98 degrees Celsius was placed in a constant pressure calorimeter of negligible heat capacity containing 100 milliliters of water. The water temperature rose from, 22.5 to 23.17. What is the specific heat of the lead pellet? Okay, now, so what we need to do is figure out a few things. First of all, it does say this thing has a negligible heat capacity, and that just means that the calorimeter is not going to absorb or emit any of the heat coming off of the hot stuff here. So what I want to do is I typically take the hot stuff and I put it on the left side because the hot stuff is going to cool down. That's exothermic. And we know that exothermic things need a negative. Okay, so I'm going to put a negative out front, and I'm going to use MC delta T is equal to MC delta T because that's Q is equal to Q. Actually, more specifically, negative Q is equal to positive Q. So we're going to have a negative M times C times delta T is equal to a positive M times C times delta T. Okay? So I have to have that negative right there. That's important. Okay? That tells me that that side is going to be emitting heat, and this side will be absorbing that same heat since they're together in the same system. So again, I left the negative up there. Let's take the hot stuff. I always put it on the left, like I said. So MC delta T. So what's our hot stuff? It says a lead pellet having a mass of 26.47. By the way, this is one problem where I would leave off units. I wouldn't necessarily get tangled up in unit calculation or cancellation here. Okay, so the mass of the lead pellet was the specific heat of the lead pellet. That's our X. Okay, specific heat of the lead pellet. And then now we got to figure out final temperature is actually this because they both come to the same ambient temperature. And you took notes on this the other day. So 23.17 is that ambient temperature minus 89.98, and we end up with a negative temperature of 66.81. I should take that back. It is a negative delta T, 66.81. Okay. Now we're going to make that equal to. This will be positive now. The mass of the water, 100 milliliters, is 100 grams times 4.18 times 23.17 minus, whoopsie, minus 22 and a half gives us 0.67. Okay, so this is 0.67. So now all we got to do is combine terms. Okay. So on the left side, I'm going to wait to apply this negative here for a second. I'm just going to take 26.47 times negative 66.81, and I'm going to get negative 1768. Okay, so this will be negative 1768 X. Okay, is equal to 100 grams times 4.18 is 418 times 0.67. Is equal to 280.1. Okay, notice I left the units off. Okay, so not too bad here. Let's flip our sign now. Okay, so let's apply this negative right here. So this negative is going to get applied. So let's get rid of it. And when we do that, we end up seeing that this is a positive number, which is exactly what we need. Okay, specific heats are not negative. And so now we just take 280 divided by 1768. And we end up with a specific heat of 0.158. X is equal to 0.158, and watch this, joules per gram times degrees Celsius, so magically it comes back. All right, so anyway, that's our answer, but that's how you do this. Now the toughest problems, and we'll probably do one of these in class, is one of these. So check, I'm sorry, that's not it yet. These are just practice problems. All right, that's it for calorimetry. We'll go over a problem where we solve for TF, final temperature is one of the tougher ones to do. So we'll do that one in class, and that's all I got. So if you have questions, email me, and take notes on the videos. See you later.